Okay, great. So thank you for the introduction and also thank you for the invitation. So today I'll talk about mainly these two papers that I put recently with my collaborators at Penn State. Uh, in those papers, we present a exciting new opportunity to study the old problems, the problems of dark matter, using the new observatory, new tool that we have, which is a gravitational waves observatories. In particular, I will try to focus on this object, GW190425, and then how to interpret this object which is quite odd in the standard model in astronomy in terms of dark matter dissipation. Okay, let's get started. So this is the summary plot of LIGO Observatory's detection as of 2 weeks ago, actually last week. So LIGO Virgo collaboration updated this list, and I think Hyung Mook, the next speaker, may have something to tell you about that. Here, I'll focus on one event. I mean, one of them is this and that. There are two neutron star, quote unquote neutron star event. First one is very famous, the 170817, which is the two neutron star collision that we have electromagnetic counterpart of that. And our guest of honor today is GW190425, which does not have any electromagnetic counterpart. Okay. And then what could that be? So GW190425, that in terms of component mass must be M1 of between 1.5 to 2.5 solar mass and M2 of between 1.12 to 1.68 solar mass. And to be able to generate the gravitational wave signal, this must be coalescence of compact objects. So that limited the list of possible scenarios into the three. So neutron star binary, or neutron star black hole binary, or black hole binary. But as a neutron star binary, it is very odd because so this is a distribution of total mass of neutron star binaries that we have detected so far in our galaxy with the X-ray observation. Those are these green lines and then PDF here. And these two lines, the orange and blue, those are the distribution of total mass that we infer from 1904 to 25. So obviously they are outside of 5 sigma. Those the red and blue, those are depending on the assumptions about their spin. So it's kind of odd that they don't fit quite into the picture that we have about the binary neutron stars. Then what about the black holes? And those masses that we measure from gravitational waves is between 1.5 to 2.5 and then 1.1 to 1.6. And from the stellar evolution model, we have quite a good understanding about the fate of main sequence stars. For example, this plot shows the fate of main sequence star as a function of its initial mass, that's a mass in the main sequence phase, and metallicity. Okay, so if their stars were born with like about 8 to 9 solar mass, and we know that it will be white dwarf of having maximum mass of 1.4 solar mass, which is a Chandrasekhar mass, and between 9 to 20, 30 solar mass, it will be a neutron star with maximum mass between 2 and 3 solar masses. That depends on the detailed structure that we don't know yet, or the equation of state in the material, in the neutron stars. So it cannot be the black holes that made out of the stellar evolution track. Then maybe people might argue that, then what about the primordial black holes? Because primordial black holes are black and gravitate, that is a perfect candidate for dark matter. So what people usually constrain is in this plot. The x-axis for those two plots are both the mass of black hole, primordial black hole, and y-axis is a fraction of primordial black hole in the dark matter. Okay, and the left-hand side is the constraint from the lack of primordial black hole signal from LIGO's O1 and O2. Oh, is the slide stuck? I don't know. I got in the chat, but can some? but I can see my slide changes. Yeah, okay, so I can go on. Okay, good. So in this O1 and O2, so the constraint from the gravitational wave observatory for the primordial black hole fraction is about, say, 1 to 10%. Okay, that's from the Maggi. And right-hand side is interesting constraint from the lack of detection of stochastic gravitational waves from nanograph. So nanograph is a pulsar timing array observation. And then we use the fact that pulsars are extremely accurate clock to monitor the timing of the pulsar for about 11 years. 1 year is about 10 to 7 seconds, so that is a 10 to 8 seconds, so they are sensitive to about 10 to negative 8 hertz. The very long wavelength gravitational waves, but they haven't detected anything. But if we do have primordial black hole with a mass about solar mass or the subsolar mass, or mass of solar mass is here, and then 10% and 1% solar mass, then to generate those primordial black hole with a large fraction, primordial density perturbation must be very large. And that large density perturbation can generate the stochastic gravitational waves that falls into the detective frequency range of nanograph. But people didn't find this so far, and then that can constrain the fractional primordial black hole. And in the mass range that we are looking at, this constraint goes like 10 to negative 4, 10 to negative 7. That is far below the gravitational waves ability, right? But then, so here comes our new idea that we thought about it, and we suggest if dark sectors, dark matters, can dissipate their kinetic energy, then they can create black holes made out of mainly dark matter. That's why we call this dark black holes. So the simple picture, the simplistic picture, although it doesn't have to be this way, any dissipative dark matter model can work here, but then the simple working model that we use is following. Instead of the single flavor of dark matter particle, we introduce some feature in the dark sector. So dark matter particle now has 3 different species, 3 different particle species. One is X, we call dark proton, C, we call dark electron, and gamma D, that is a dark ENM, dark photon. Okay? So in this model, we have three different species, and then we have 4 different parameters. Parameters being the mass of dark proton, the mass of dark electron, and the coupling constant between dark charge and dark radiation, and the temperature of dark photon. Okay. The reason why I need this setup is because I want dark matter to lose its kinetic energy, to dissipate. Why is that? It's very easy to understand. So in the standard model of structure formation, we have about 5/6 of matter in CDM and 1/6 of matter in baryons. Okay, so when the halo first formed, we do have kinetic equilibrium of CDM and baryons all together in the halo. But later, we all know that we have a galaxy at the center, and our skirt is a halo. So what makes this difference? It's because baryons can dissipate energy, therefore, to lose its kinetic energy to sink toward the center of the gravitational potential, while CDMs cannot. By introducing this dark atomic theory, what we want to do is to introduce the channel that dark matter can lose energy, therefore collapse toward the center and do what baryons would do, meaning forming the structure. Of course, we cannot choose this arbitrary parameter space, because if dark matter has this feature, and that we do have to revisit all the cosmological calculations that we have done so far. For example, because dark matters that had interacted with dark radiation, we do have dark recombination. Okay, this is for one particular parameter choice, the dark proton of 16 GeV, dark electron of 140 keV, and dark photon temperature being 2% of CMB temperature. In that case, dark recombination happens at around redshift 50,000, very early time. Okay, then we had to calculate the the detailed recombination, I think here we use a Peebles 2-level calculation. Also, we have to calculate the visibility function. And associated with that is dark acoustic oscillation scale. In this particular example, the dark acoustic oscillation scale is very small, which is about 0.2 megaparsec or 20. And also dark matter has dissipate, or the erase is perturbation due to the coupling between dark matter and dark radiation. They introduce a Sikh damping scale, which is about 240 kiloparsec. So there are rich kind of physics and then cosmological consequences there, and that can, for example, help to address the, say, small scale problem, because we naturally suppress the power on small scale using the dark Sikh damping. That may help to address the Hello, can you hear me now?
Yes, you're back. Yeah. So please
Okay,
continue.
I'm back. Great. Great. Okay. So I was here. Yeah, suddenly all the window disappeared. Okay, so then we had this one criteria, because we know that large scale structures seem to obey the outcome of cold dark matter features on very large scale, right? We do have filamentary structure, and we do have galaxy clusters, we do have galaxies and galactic halos. So what we want to do is that we don't want to spoil the great success of large scale structure. So one way to do it is to require something like a Ridge-Ostrich criterion, saying that the cooling time, the efficiency for a baryon to lose its energy must be very, very, very inefficient for the halos whose mass is greater than 10 to 11 solar mass, right? The requirement is that cooling time for those halos must be much, much longer than the age of universe, means that cooling basically shuts off. But for small halos, cooling is very efficient. We can sufficiently cool the dark matter to make the collapsed object, okay, such as dark stars and dark black holes. All right. And here there are two important mass scales. First of all, we have Chandrasekhar mass. And if you look at the equation for Chandrasekhar mass, it's very interesting, because this is a fundamental quantity. I mean, this mass scale of 1.4 solar mass involves all the fundamental constants except for the proton mass. So the Chandrasekhar mass is inversely proportional to proton mass square. That's because the Chandrasekhar mass is the maximum mass at which the degenerate star can hold up against the gravity, right? And then the degenerate pressure is increasing if you have more number of particles, right? And the number of electrons basically is determined by number of proton if you assume the charge neutrality, which is very natural. That's why Chandrasekhar mass must depend on the proton mass. And the second mass scale is called the opacity limit. So particles, or the baryons and dark matter, when they form stars, they first lose their kinetic energy to collapse, but they cannot arbitrarily collapse the high density, because if the density increase beyond a certain point, then the opacity is increasing as well. Therefore, you cannot lose energy. So then therefore, there's a transition between the isothermal collapse and then adiabatic, say, expansion. Okay, and then there's a minimum mass scale in transition scale between those two, the different physical processes. That is M, the black hole minimum, that I call it opacity limit. That is old calculation by Rees or the Low and Lindenbell, but that gives us order of magnitude correct mass scale of, for example, POP3 star. Okay, and this mass scale is a very interesting feature because that depends on the temperature of hydrogen molecule, the dark hydrogen molecule. Okay, and dark hydrogen molecules ground state and the first excited state energy level is basically determined by rotational energy level, and that is, as you know, the L square over 2I is inversely proportional to momentum of inertia. And then if you have heavy proton, then we increase the momentum of inertia for the dark hydrogen. Therefore, we can shrink the energy gap in the dark molecule very, 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 very small temperature. That means that we can make very fine energy gap that can be translated into the very cold dark matter stars. That means the dark matter star can be very light. Okay. And what we did is that we took a result from the population 3-star formation simulations, because here our setup, we have dark proton, dark electron, and dark photon that goes exactly parallel to the POP3 very extremely metal-poor star formation process. So we took their result, and there are rich literature about POP3 binary formation and the POP3 binary parameter distribution, like eccentricity or the semi-major axis distribution. We took those numbers and then rescale the mass scale of the opacity limit with the dark matter's cooling scale and the mass scale. And then we got this graph of the dark black hole mass distribution as a function of its fundamental physics quantity, such as the proton mass. So here I plot 4 different proton mass. The green is 50 GeV, 100 GeV, 150 GeV, 200 GeV. So standard model proton is 1 GeV. So those are the very heavy, like 50 times heavier than the standard model protons, and then 200 times heavier. As you move to the heavier side of dark matter, then the spectrum of dark matter black hole distribution pushed to smaller and smaller mass. And then here we can make the black hole mass of 1 solar mass and below very easily. Okay. And these very tiny light black holes can be detected by LIGOs and advanced LIGO and then LIGO-Virgo and then Einstein telescope. Here, the left-hand side plot is the Chirp mass. As a function of Chirp mass, the horizon distance, which is the A sigma detection limit. So for the solar mass black hole binaries, and then current LIGO can reach out to 100 megaparsec. And the full upgraded advanced design sensitivity is a little bit beyond, and then Einstein telescope, of course, can detect that to like 10 gigaparsec. So subsolar mass black holes are within our technological reach, and then that has far and the implication far beyond just the stellar evolution, because if you detect that, you can say something about the dark matter population. Currently, I think that's the only possibility to make like 10% solar mass black holes. Okay, and that is the distribution of Chirp mass, and we also calculated the rate at which we detect those black holes binary, and then for the advanced LIGO full upgraded, we expect to have 1 to 10 event of those. So those are quite encouraging. Okay, and then we take this result and we try to reinterpret the gravitational waves GW190425 by using this new framework. Okay, of course, GW190425 doesn't have to be dark black hole. If this particular event is not dark black hole, then we have just a constraint we have constrained the parameter space in this minimum mass of black hole that is basically given by the opacity limit and the fraction of dark matter black holes within dark matter. Okay, but if GW190425 really turns out to be a dark matter black hole, what you can do is we can connect this minimum mass of those black hole population into Chandrasekhar limit of dark sector, and then we excluded the baryonic Chandrasekhar mass by 99.9% confidence level. So if GW190425 turns out to be a dark black hole, then the conclusion, unambiguous conclusion for this interpretation is that dark matter proton mass, mx, must be greater than about 1 GeV. Okay, of course, this is not the only place that we can place a constraint. And this dissipative dark matter model, the one central quantity is called the cooling function. The cooling function is the rate at which this dark matter can lose energy. And then this cooling function depends on primarily depends on temperature, because temperature determines the ionization state of this dark atomic structure. And here I have this plain vanilla atomic cooling function here as a black. And this green region is to create enough of dark black holes within a halo of 10 to 5 to 10 to 9 solar mass. Okay, there are regions because we have different redshifts. And then if dark matter has this nice feature, but we don't allow too frequent interaction or too much of the scattering of dark matter. For example, black cluster constraint must be satisfied, and here the reddish region shows that constraint. So depending on the parameter that we assume for the black cluster collision, and then it can be satisfied. And also on small scale, and this the brown region is a region that if the cooling function of the scattering of dark matter is so frequent, then any collision will completely disrupt the dwarf galaxy. Okay, and this may, although we do have some dwarf galaxies, we don't want to destroy all the dwarf galaxies, but this may not be a too bad thing, given that we observe only very few number of dwarf galaxies. But the interesting thing is that we can combine the result from the gravitational wave observation with all the other astrophysical consequences, and then can constrain the regional parameter space of this cooling function. Okay, so let me conclude here. So gravitational wave provide an exciting new avenue for studying dark matter. It's a new tool for the old problem, and we connect these exciting two fields. And then also interesting feature is that this use the only guaranteed property of dark matter. Dark matter, we have then direct search, indirect search, but dark matters do not have to talk to the standard model particles. But here, we use a gravitational wave and the energy dissipation. The only fundamental interaction that goes into here is gravity and dark matter dissipation, okay? And then, as I showed you before, if the GW190425 turns out to be dark black hole binary, then that tells us that dark proton mass must be heavier than the standard model proton. And by combining the other astronomical constraint, we can also constrain the cooling function itself. Okay. And as I know, the subsolar mass black hole binary search is ongoing in the Virgo collaboration. And immediate thing that we have to do, because this paper came out last week, is to extend our analysis, including all those new black hole binaries that they found in the O3A event. Thank you very much for your attention.
Okay, thank you for this very inspiring talk, also highlighting this peculiar event 190425. So I would like to open the floor, as we would normally say, to questions. So I will also check if somebody is raising a hand. but you are encouraged actually to submit your questions to the Google Doc. I see one question from Yosushi Suto, so please go ahead.
Hi, Donghui.
Well,
Yes, I really enjoy. So this is quite interesting talk. So but I'm not so familiar with this case. So I think so. This is of course this is a kind of some toy model to just to discover a possible dark sector in our universe. And when you say that so dark proton and a dark electron or something, is there any sort of so particle physics or something elemental particle physics behind it, or actually, my question is, so this is quite interesting. If you assume this kind of structure, you might be able to put some limit on the mass of the dark proton, but I do not understand what it means. Maybe so this is a frequent asked question, but so I'm very interested to just hear.
right. So, frankly speaking, I don't have any particle physics motivated model for this right now, but I think this is more phenomenologically motivated because I mean we know that what baryon does and dark matter does not do is cooling, right? That's energy dissipation. And then what if dark matter, at least some part of dark matter dissipate the energy to form structure, right? That general theme has been studied quite vigorously recently. For example, Risa Rendell had her model that dark matter collapsed to form some disk. And then we are living in somewhat different parameter space than her. And then we search for the other possibility using the black holes. But I don't.
So once you identify some kind of black hole in the universe, is there any possible to just to distinguish from the primordial black hole or some standard black hole with some unknown formation mechanism?
Right. Yeah. I think, yeah, I discussed that with Misao a lot. And then he suggested maybe spin distribution may be very different for the primordial black hole and this black hole. And also for the primordial black hole, I think this graph is somehow telling us that we cannot have so many primordial black holes in the universe. And this nanograph constraint shows that, I mean, if you do have those primordial black holes, then we do expect to see some stochastic gravitational waves that we didn't see. So there are some challenges in primordial black hole in that particular mass range.
Okay, thank you very much. I really enjoy it. Okay, thank you.
Thank you. Looking forward to your talk.
There's room for a few more questions, so please raise your hand if you wish. Okay, I have one question myself. How do you, if you like, limit the number of relatively low mass, you call them dark black hole binaries? Because if you have too many, obviously you would give a tremendous input to the stochastic background of gravitational waves. And we should ultimately be able to constrain it through that channel as well.
That's right. It will make the primordial, the stochastic gravitational wave as well. Yeah. I haven't looked at that particular case, but yeah, I think that's certainly a possibility. Yeah.
Well, I would say it's a challenge, I think, to make sure that you don't overproduce a background.
Right, sure. Yeah, and here, as I said, is F dark black hole. That's a fractional dark black hole locked in fraction of dark matter that is locked in the dark black hole. Just like that, every baryon ends up in star. Not every dark matter ends up in dark black hole here. And then here our fraction is very small. It's 10 to negative 5 to 10 to negative 3. So the stochastic gravitational waves may be produced, but it may not be too much because this fraction is so small. Only like 0.1% to 10 to negative 5 of dark matter form the black holes. And so we estimated the expected Bondi accretion around this black hole. So if you can have those signal, and then that was quite small as well.
Okay.
I think Hosung has a question in the chat.
I'm sorry?
The Hosung asked the question in the chat, and he said, any clue to know whether this particular source is a binary black hole? Yeah, but I think that's...
Yes, can you give a very short answer to this? We are getting out of time.
So one clear cut is the subsolar mass. If you have binary black hole, very light, and there could be, I think, either primordial black hole and dark matter black hole. And I think the secondary is perhaps the spin distribution, or if you have in a lucky situation that we have millions of them, and you can cross correlate that with a known halo distribution. And primordial black hole doesn't have to be in the halo, but I think dark black hole formed within dark matter halo must follow dark matter halo distribution. So that's very futuristic possibility, but there are ways.
Okay,